What's going on, guys? Justin here, and welcome back to the fourth math major example video following our course on differential equations. Today's video is going to be on non-separable linear differential equations and some substitutions and tricks to get you through those. So let's get into our definitions before we do some problems. Now for today's video, I'm actually using a slightly different recording process. So if you see me in the background back here, it's a little bit different than it usually is. I'm planning on fine-tuning it in the future, but for today's video, we're stuck with it how it is, so don't be frightened if you're looking at the screen too hard and you see me in the background because it's a little less obvious than it usually is. But anyway, so let's get into our two definitions for today's video. So like I said earlier, our video for today is on linear non-separable differential equations. So we're going to have two definitions for today's video. The first definition is going to be the definition for a Bernoulli equation. Sorry if I mispronounced that. So our definition for a Bernoulli equation is as follows. For some little r, which is a real number, where little r is not equal to 0 or 1, we have that any equation that can be written in the form y prime plus p of x times y equals f of x times y to the r is a Bernoulli equation. So this is going to be a specific type of non-separable linear differential equation in which we have a process for. And then we have the following definition for a homogeneous equation. We say a linear equation is homogeneous if it can be written in the form y prime plus p of x times y is equal to 0. Now there are actually two commonly accepted definitions for homogeneous. One is the one I've written out here, and the other is a function that can be written as y over x or x over y. But for the purposes of this video, when I say homogeneous, I mean this definition right here. So now that we have our definitions out of the way, let's get into our examples. Okay, so problem number one says y prime plus xy is equal to x times y squared. So let's go ahead and recall the definition for a Bernoulli equation. And we can see that this equation is in the desired form. Now for Bernoulli equations, the solution process is to solve the associated homogeneous equation, which in this case will be y prime plus xy is equal to 0. And then we will use that solution as a substitution, which will solve our entire differential equation. So let's go ahead and solve this homogeneous equation to start. So we can begin by noting that this differential equation is indeed separable. So let's go ahead and separate our variables. So we'll subtract our xy to the other side, and that will give us y prime is equal to negative xy. Then we'll divide our y prime over, and we can take our antiderivatives. So doing that will give us the following. We will have that the antiderivative of dy over y is equal to the antiderivative of negative x dx. All right, so after taking our antiderivatives, we will get the natural log of the absolute value of y on the left-hand side, and that will be equal to negative x squared over 2 plus some constant c. Next, we're going to exponentiate both sides to solve for y, and we will get that y is equal to e to the power of negative x squared over 2 plus c, which we can split up in the following way as e to the negative x squared over 2 times e to the c, and we can rewrite this e to the c as a constant, which we're just going to call c. It gives us our final definition for y here. We'll have that y is equal to e to the negative x squared over 2 times c. Now we're actually going to leave off this c here, as the purpose of solving this homogeneous equation was to get a substitution for y, and the c is not relevant for that. So now that we've solved our associated homogeneous equation, we can write out our definition for y naught, which is going to be equal to z times what I've underlined in blue here. So we'll get y is equal to z times e to the negative x squared over 2. The general rule for the substitutions associated with these types of problems is you take z and you multiply it by whatever you get minus the constant from the homogeneous equation. So let's go ahead and plug that into our original differential equation. So if you'll recall, our original differential equation is y prime plus xy is equal to xy squared. So this y naught will be taking the place of y in this equation, but let's go ahead and derive a definition for our y prime, and we'll do that using the product rule. So we'll have z prime times e to the negative x squared over 2, and when we take the derivative of e to the negative x squared over 2, we're going to pick up a minus x, so we'll have z prime times e to the negative x squared over 2 minus x times z times e to the negative x squared over 2. So let's go ahead and make these two substitutions. So first, substituting in for y prime, we will have z prime times e to the negative x squared over 2 minus x times z e to the negative x squared over 2. And then we have plus xy, so we'll get plus x times our definition for y, which is z times e to the negative x squared over 2. And that's going to be equal to x times y squared, which is going to be equal to x times z squared times e to the negative x squared. Now, if you did your substitution right, you should notice that you have cancellation on these middle terms here, which in fact we do. So this negative xze term is going to cancel, and it'll leave us with the following differential equation. We will have z prime times e to the negative x squared over 2 is equal to x times z squared times e to the negative x squared. And you'll notice that that differential equation is indeed separable, so let's go ahead and separate our variables. So after separating our variables, we will get that z prime over z squared is equal to x times e to the negative x squared over 2, which means we can equate the following antiderivatives. We'll have the antiderivative of 1 over z squared dz is equal to the antiderivative of x e to the negative x squared over 2 dx. Evaluating those antiderivatives, on the left-hand side, we will get negative 1 over z. And on the right-hand side, let's make the following u substitution to solve. So we'll have that u is equal to negative x squared over 2. So that will make our du equal to negative x dx. So substituting that into our integral will give us negative the integral of e to the u du. And that is, of course, going to be equal to negative e to the u plus some constant c. So let's go ahead and cancel our negatives on both sides here. So that will give us 1 over z is equal to e to the u plus some constant c. And on doing our substitution will give us that 1 over z is equal to e to the negative x squared over 2 plus some constant c. And solving for z gives us 1 over e to the negative x squared over 2 plus c. If you recall, our substitution was y is equal to z times e to the negative x squared over 2. So if we multiply the right-hand side by this e term here, we can write a y on the left-hand side. So we'll get y is equal to e to the negative x squared over 2 over e to the negative x squared over 2 plus some constant c. And we can multiply this by e to the x squared over 2 over e to the x squared over 2, which will give us the following final answer for y. We have that y is equal to 1 over 1 plus c times e to the x squared over 2. So let's go ahead and jump into our next problem. So the problem for number 2 is y prime minus 3 over x times y is equal to x to the 4th times y to the 1/3 power. So following the same solution process as before, let's begin by solving the associated homogeneous equation, and that will be y prime minus 3 over x times y is equal to 0. And this equation is, of course, separable. So once we separate our variables, we will get the following. We'll get that y prime over y is equal to 3 over x, which means we can equate the following antiderivatives. We will have the antiderivative of dy over y is equal to the antiderivative of 3 over x dx. And evaluating those antiderivatives is rather simple. We will get, for the left-hand side, we will get the natural log of the absolute value of y, and for the right-hand side, we will get 3 times the natural log of the absolute value of x plus some constant c. We're going to go ahead and exponentiate both sides to solve for y, and we'll get that y is equal to x cubed times c. So we can write out the following substitutions for this Bernoulli equation. We'll have that y naught is equal to x cubed times z, which means that y naught prime is going to be equal to z prime times x cubed plus z times 3x squared. So let's go ahead and substitute that into our original equation. So we will have z prime times x cubed plus z times 3x squared minus 3 over x times x cubed z is equal to x to the 4th times x cubed z to the 1/3 power. And we can see that we've done our substitution right, as our middle two terms here will cancel out, which will give us the following separable differential equation. We'll get that z prime times x cubed is equal to x to the 4th times x cubed z to the 1/3 power. And we will go ahead and rewrite this right-hand side as x to the 5th times z to the 1/3 power to make our separation of variables easier. And once we divide that x cubed over and that z to the 1/3 over, we will get the following. Z prime over z to the 1/3 power is equal to x squared, which means we can equate the following antiderivatives. We'll get that the antiderivative of dz over z to the 1/3 power is equal to the antiderivative of x squared dx. Evaluating those antiderivatives will give us that 3z to the 2/3 power over 2 is equal to x cubed over 3 plus some constant c. And multiplying by 2 and dividing by 3 will give us the following definition for z to the 2/3 power. We'll have that z to the 2/3 power is equal to 2x cubed over 9 plus some constant c. And if you recall, our original substitution was that y is equal to x cubed times z, which means that y to the 2/3 is equal to x squared times z to the 2/3, which means we can multiply the right-hand side of this equation by x squared to set it equal to y to the 2/3. So we'll have that y to the 2/3 power is equal to 2 times x to the 5th over 9 plus x squared c, which means we can write our final definition for y. We will have that y is equal to the quantity 2x to the 5th over 9 plus x squared times c, all to the 3/2 power. So let's move on to our next example. All right, so number 3 says x squared times y prime plus 2xy equals y cubed, and we have this initial condition y of 1 is equal to 1 over the square root of 2. Now this is not currently in the form that we need for it to be a Bernoulli equation, but let's see if we can manipulate it into being, and in fact we can by simply dividing by x squared. So rewriting the equation after dividing by x squared, we will get that y prime plus 2y over x is equal to y cubed over x squared, which means we can solve the following related homogeneous equation. We will have that y prime plus 2y over x is equal to 0, and that is in fact separable. And once we separate our variables, we will get that y prime over 2y is equal to -1 over x, which means we can equate the following antiderivatives. We will have that the antiderivative of dy over 2y is equal to negative the antiderivative of 1 over x dx. Taking the antiderivative of the left-hand side is going to give us 1/2 times the natural log of the absolute value of y. And taking the antiderivative of the right-hand side, we're going to get negative the natural log of the absolute value of x plus c. Multiplying by 2 and exponentiating both sides will give us the following definition for y. We'll have y is equal to x to the -2 times c, which allows us to write the following substitutions for this Bernoulli equation. We will have that y naught is equal to x to the -2 times z, which means that y naught prime is going to be equal to z prime times x to the -2 minus 2 over x cubed times z. So let's go ahead and substitute these two into our original equation. Doing so will give us z prime over x squared minus 2z over x cubed plus 2 over x times 1 over x squared z. And that's going to be equal to 1 over x squared times the quantity 1 over x squared z to the 3rd power. So we can see that we can cancel these two middle terms here as we want, and we can also multiply by x squared to clear the denominators in the remaining terms, which will give us the following. We'll have z prime is equal to 1 over x to the 6th times z cubed, which after separating our variables gives us z prime over z cubed is equal to 1 over x to the 6th, which means we can equate the following antiderivatives. We'll have the antiderivative of dz over z cubed, and that's going to be equal to the antiderivative of dx over x to the 6th. Taking those antiderivatives is going to give us 1 over -2 times z squared is equal to 1 over -5 times x to the 5th plus some constant c. Next, we're going to use our initial condition to solve for our constant c. So if you recall, y of 1 is equal to 1 over the square root of 2. And we made the following substitution for y. Y naught is equal to x to the -2 times z. We're going to use these two equations to see what the value of z will be with this initial condition. So we will have that 1 over the square root of 2 is equal to 1 to the -2nd power times z. But that, of course, means that z of 1 is also equal to 1 over the square root of 2. So let's go ahead and make that substitution here. We will have that 1 over negative 2 times 1 over the square root of 2 quantity squared is equal to 1 over negative 5 times 1 plus c. But 1 over the square root of 2 squared is just going to be 1/2, and 1/2 times negative 2 is negative 1. So that will give us negative 1 is equal to negative 1/5 plus c. But that means that c is simply equal to negative 4 over 5. So let's go ahead and plug that into our original equation. We will have that 1 over negative 2 times z squared is equal to 1 over negative 5 times x to the 5th minus 4 over 5. We can go ahead and rewrite the right-hand side of this equation to be 1 plus 4 times x to the 5th over negative 5x to the 5th. That means that after multiplying by negative 2, we would get that z squared is equal to 5x to the 5th over 2 times 1 plus 4x to the 5th. And then we can take the square root of both sides to solve for z. That means that z is equal to the quantity 5x to the 5th over 2 times 1 plus 4x to the 5th to the 1/2 power. And from our initial substitution, we said that y is equal to x to the negative 2 times z. So if we multiply the right-hand side by x to the negative 2, we can equate it to y. So we will have that y is equal to 1 over x squared times that big quantity we already wrote before, 5x to the 5th over 2 times 1 plus 4x to the 5th, all to the 1/2 power, which is the solution to this differential equation. These next two differential equations we are going to solve with some basic substitutions. So for number 4, we have that y prime is equal to y plus x to the negative y over x, all over x. And we are going to be making the substitution y is equal to u times x to solve this differential equation. Well, since we have y is equal to u times x, that means that y prime is going to be equal to u prime times x plus u. So once we substitute that into this equation, we will get u prime x plus u is equal to ux plus x times e to the negative ux over x, all over x. But we can see that a lot of stuff cancels on the right-hand side of that equation, and that will leave us with u plus e to the negative u. But we can cancel this u on the right-hand side and this u on the left-hand side and get u prime x is equal to e to the negative u, which gives us a separable differential equation. Once we separate our variables, we will get that u prime over e to the negative u is equal to 1 over x, which means we can equate the following antiderivatives. We will have that the antiderivative of e to the u du is equal to the antiderivative of 1 over x dx. And the antiderivative of e to the u du is obviously e to the u, and that's going to be equal to the natural log of the absolute value of x plus some constant c. Then we can take the logarithm of both sides, and we will get that u is equal to the natural log of the absolute value of x plus some constant c. And if you recall, our original substitution was that y is equal to u times x. So what we have to do is multiply this right-hand side by x to get our definition for y. We will have that y is equal to x times the natural log of the absolute value of x plus c as our final answer for this differential equation. So for our fifth and final differential equation for this video, we will have that y prime is equal to the quantity x minus y plus 1 squared. And the substitution we are going to be using is we are going to let v equal x minus y plus 1. And that means that dv over dx is going to be equal to 1 minus y prime, which of course means that y prime equals 1 minus v prime. So let's go ahead and make that substitution. So on the left-hand side, we will have 1 minus v prime, and that is going to be equal to v squared. Next, we can solve for v prime. So that will give us v prime is equal to 1 minus v squared, which gives us a separable differential equation. We will have 1 over 1 minus v squared dv is equal to dx. Now we can take the antiderivative of both sides. I'm not going to go through the antiderivative of the left-hand side, but you can do that for homework if you want. So after taking the antiderivative, you will get the following. We'll get 1/2 times the natural log of the absolute value of v plus 1 over v minus 1, and that is going to be equal to x plus c. Then we're going to multiply by 2 and exponentiate both sides, so we will get that the absolute value of v plus 1 over v minus 1 is equal to e to the power of 2x plus c, which we can rewrite as v plus 1 over v minus 1 is equal to c times e to the 2x. From here we can undo our substitution, and the left-hand side will become x minus y plus 2, and the bottom will be x minus y. And that's going to be equal to c times e to the 2x. From here we can clear the denominator, and we'll get that x minus y plus 2 is equal to c times e to the 2x times x minus c times e to the 2x times y. And with this we can separate our variables, and we will get that y times c times e to the 2x minus y is equal to c times e to the 2xx minus x plus minus 2, and we can factor out a y from the left-hand side to get y times c times e to the 2x minus 1 is equal to c times e to the 2x x minus 2. And dividing those x terms over to the right-hand side will give us our final solution to this differential equation. We will get that y is equal to c times e to the 2x times x minus 2 all over c times e to the 2x minus 1. I'm not sure if there's a way to simplify that, but if there is, please post it in the comments, and that's a good place to stop.